Okay, we're recording.
Hey, thanks a lot.
All right, thanks.
Hey, everybody, really sorry about that. Okay, I'm going to try and share a screen here. Any questions before we start? What I thought we'd do is a real quick review of last week. And then we've got, today is really extensions of what I talked about last week. Last week's the core material. And really everything from today is extensions of that. So any questions before I start? Okay, well, let's do everybody see a quiz on the screen? Okay, so let's talk through this real quick. Usually I've just given people a few minutes to think about these things, but why don't we just talk through this briefly? And this is meant to be a quick review of last time. So generalized linear model, when would you use a generalized linear model?
Typically when you have non-normal data.
When you have non-normal data. Anybody like to elaborate?
And a simple transformation would not work in this case.
A little louder, Randy.
And the simple transformation of the data would not work in this case.
Yeah, when a simple transformation would not work. Okay, keep going. I want some more elaboration. Non-normal data, any kind of non-normal data?
Non-normal
exponential family.
Exponential family, right. So it's not any kind of non-normal data, that very specific set of distributions that make up exponential families. So if you have data with a really, a few really wild outliers or negatively skewed or bimodal, you may be able to find extensions of generalized linear models, but a generalized linear model is not meant to handle that situation, okay? It's for these specific kinds. Most common ones are normal, Poisson, binomial, and gamma. Negative binomial, I guess we'll see, generalized gamma. So there's a few others, but this really is the set of things. So skewed positive distributions are well handled by this. Count distributions are typically well handled by this, but it is a specific kind of non-normal distribution, okay? And one thing I mentioned last time is you can regard generalized linear models as a way to do data analysis with exponential families. So all the stuff you saw last year in theory about exponential families, that didn't do any covariates, it didn't do any random effects, it didn't do any of the stuff we really are using, we really need to do when we do statistical analysis. So, so that's the restriction on these. Any question on that? Okay, can you write this normal regression model in generalized linear model form? Do you remember how that's done?
Can you just add the G link function either to the Y side or the G inverse to the other side, the right side?
You can, but there's no link function here, or the link function identity, whatever you want to, however you want to think of it. Okay, so that's not quite what I was after. Okay, the big difficulty with extending this model to non-normal outcomes, to exponential family outcomes like counts and positive values, is that plus epsilon out there. As long as you've got that plus epsilon, you'll never be able to keep the models in the right sample space. Okay, so if your x prime beta is just a number, positive, negative, continuous number. So how are you going to get a count or ensure that the result is positive with a plus epsilon? There's no epsilon that will do that for you. So the other way to do it, the easy way to remember this is instead of y equals, it's y is distributed as. Okay, and as soon as you write it that way, then you can replace that n by pretty much any exponential family distribution. Okay, Poisson, gamma, binomial. Okay, so that's the key trick for generalized linear models is to replace that that equals and the plus sign, the plus epsilon, with is distributed as. Okay, another way to think of it is, remember before, if we had skewed data, we might transform the y's. Now we're going to transform the mean. We won't be transforming the y's. Okay, any question on that idea? Okay. What are the three components of every generalized linear model? The three things you need to specify to any software in order to fully specify a generalized linear model.
Random component, systematic, and the link function.
Good, exactly. Random component, in other words, the outcome distribution. The systematic component, in other words, the linear predictor, x prime beta, all your covariates and treatments and such. And the link function, which tells you what scale you're on. Linear, logistic, log, okay? Those three things, and you remember we showed you software last time for SAS and R. Every one of those, you had to specify these three things and nothing else, okay? So those are the three things that make up a generalized linear model. Questions on that? Okay, write down a Poisson generalized linear model. We just got some hints up here from this one. So what would you have to change to make this one Poisson?
You change normal to Poisson distribution and then you'd exponentiate your
Yep.
predictor.
Yep, exactly. Those two things. You change the normal to Poisson, which gives you count observations. But then you have to make sure the mean of the Poisson is non-negative or positive. So one nice way to do that is to exponentiate the linear predictor. And Poisson only has one parameter, so we wouldn't have a sigma squared there. Okay, so there you go. Y, and again, the key is it's not y equals, it's y is distributed as. Poisson with mean e to the x prime beta. Okay, question about that? If you want binomial, you would do the same sort of thing. Replace the Poisson by binomial. There you have another parameter, n. So sometimes an exponential family distribution will have another scale parameter, but Poisson does not. Question on that? Okay, gave that one away. What is the link function link? Back up here, what is the link function? The link function is actually log, but inverse of exponential. And what is it linking?
The linear predictor to the outcome.
The linear predictor to the outcome. What about the outcome?
The mean of the
Yes,
outcome.
exactly. The mean of the outcome distribution, right? So it's taking the linear predictor, x prime beta, and linking that to the mean of the outcome distribution. And see, this is a key thing because the mean of the outcome distribution, that's kind of a physically well-determined thing, right? You can just take the mean of your observations, and that's an estimate of the mean of your outcome distribution, okay? So that's a observable thing. And so are the covariates. So those are the two observable pieces of your data, but they have to be linked to the distribution. So in this case, they're linked to the probability distribution through the mean. Okay, so a link function links covariates and mean outcome. And then finally, this one, which we did last time, sketch data simulated from a Poisson generalized linear model or Poisson regression with one covariate and a positive slope. You remember what that one looked like? What are the main features of it? What values will y take on? The only values can be non-negative integers. What will the pattern look like? What will the mean pattern look like? Straight or curved?
Curved.
It'll be curved, right? Because of the exponential function. And what about the variance? What do you know about the Poisson distribution?
The mean and variance are the same. So since the mean is curving up, the variance is also increasing as we move up.
Exactly. The variance has to follow the mean. So it'll look like this. There's your non-negative counts. See the horizontal stripes are the counts, only at integers. Increasing, it's curved because of the exponential function. And look at the variability here at 6 compared to the variability at 1 or 2 or 0 down here, okay? So all those features are built into the generalized linear model. Everybody okay? I did post that handout online at this handout I had last time about simulating this data. I'd forgotten to last time, but it's on there now. Anybody have questions about any of this? Okay, so that's a pretty quick. Any questions about things we did last time on generalized linear models? I'll grab up some notes here quickly. I'm gonna, let me think about this. I have to remember how I share things here. Oh, let me share this one real quick. So this is the outline for today. Last time we talked about almost all of our time, we talked about the serial data, and we spent almost all of our time on the key aspects of the models. We also talked about estimation. What is it that makes this model these models more difficult to estimate than linear regression? It's actually two things. It's that it's nonlinear because of the exponential function and the unequal variance. And both of those have to be adjusted for in the estimation. And that algorithm is called, it's an application of maximum likelihood, but the algorithm is iteratively reweighted least squares. And the reason that's important, I think the thing I'd take away from that is just that it's iterative. You can't just do a single matrix calculation. So you'll notice the software will give you lots of iterations. And if it doesn't converge, you'll know there's trouble. All right, anything there? We talked a little bit about diagnostics. Well, inference is actually pretty easy because it's all the stuff you're familiar with. Likelihood ratio tests, walled confidence intervals, and AIC, BIC, all of those things that you used before still hold for all exponential family distributions and all generalized linear models. So we kind of get that part for free. Diagnostics I didn't say very much about, but you know, there's residual plots and things for generalized linear models. I honestly don't find those so useful, and it's because because of the outcomes. You know, think about logistic regression. Residuals are always something like y minus predicted values. Well, the only values of y are 0 and 1. So you get these very crazy looking residual plots. Maybe my eye has just never been trained to them, but I have not found them as useful, anywhere near as useful as in linear regression. But that may just be me. And then at the end, we talked about software. I gave you software in R and SAS. And then interpretation. Remember, we talked about, let's see, mean differences for a linear link, rate ratios for a log link, and odds ratios for logistic link. Okay, so it's the link that determines the interpretation of your betas. Questions on any of that stuff?
I have a quick question, Gary.
Sure.
So for when you fit these generalized linear models, do you typically scale your covariates so that they're on the same scale? Would that affect, so if you have covariates on different scales, would that affect your variance? Because you'll be increasing your mean?
Yeah, good question. It actually doesn't, it's not necessary to scale the covariates in general. And you just need to you do need to keep track when you interpret them. So for instance, if your X is in units of hours or say months, for example, then your beta is in terms of change in Y per month. So you need to pay attention to that, but otherwise, no. The only time it's necessary is if you get into more, and this is kind of my personal experience, if you get into more complex models with, say, random effects, which we'll talk about when I come back in a few weeks, those are much more difficult to fit numerically. And so having covariates with large values can throw those off. So for instance, if I had time as a covariate and time was in days and my time period spanned years, then X would go into the thousands. I would usually rescale that as months or years. But otherwise, no, not any need to rescale those.
Okay, thank you.
Yep, what else?
I was wondering with the SAS software, when I'm running models, is often saying that they're using the quasi-Newton method. And I was wondering if you knew what that was in reference to.
Yeah, so that has to do with this is an iterative algorithm, and it's there's a couple derivations. I think I might have put a handout into onto the website. I had Matt post a handout. There's a couple ways to derive the iteratively reweighted least squares algorithm. One of them is based on the Newton approximation or Newton-Raphson method for numerically optimizing a function. And so that's what it's referring to. It's using a numerical version of the Newton-Raphson algorithm. And what that kind of does is a really smart search. It looks at the first and second derivatives, decides which direction it should take a step and how big a step it should take, and it goes there. And then it takes another look at which direction and how big a step it should go. Yeah, so that's what that refers to.
So then that is separate from whether it's estimating ML or REML, for instance.
Okay, yeah, good question. Yes, all of those algorithms are versions of Newton-Raphson. Depending on the situation, there need to be other modifications to it. But yeah, those are all versions. The base, the core of those algorithms is all the idea of Newton-Raphson. Yep. And they're, if it's maximum likelihood, so this is maximum likelihood. The estimation is maximum likelihood. The difference is there's no closed form. So the only way to get that estimation is with an iterative algorithm. Okay. What other questions? Okay, I'm going to go jump over to the notes now for today. I sent Matt an updated version. I had done some red highlighting in the notes, and so I've continued that onto the material for today. So this would be the notes version 2. Okay, everybody seeing it? Okay, so I'm going to go down here. Okay, 3.9, section 3.9, which looks like page 13. Okay, here's the deal on these. Generalized linear models are for exponential family distributions, but take a look at the Poisson distribution. Poisson has its sample space as 0, 1, 2 up to infinity, okay? And what's the one fact, well, I can't ask you something about my memory, but I can tell you the one thing I remember about a Poisson distribution is the variance equals the mean. So what does that tell you about analyzing real data with the Poisson distribution? It's going to be super restrictive, right? Real data don't know about that restriction. So there's no particular reason why real data would always maintain a variance equal to the mean. That's a theoretical relationship, it's not an empirical one. So that's where you get into trouble with with trying to do data analysis using, say, a Poisson or a binomial. Those are very, very restrictive relationships. Okay, here, think about this. Imagine somebody asked you to analyze normal looking data, but they said the variance always has to be equal to the mean. Well, you'd never try to do that, right? So you really wouldn't want to do that with a Poisson either. So the point of this over and under dispersion is that real data tend not to follow these restrictions. And this is going back decades to when I first saw this material. I remember seeing, we learned about generalized linear models, and then we learned about over and under dispersion. And I thought, oh yeah, I suppose in some kind of pathological cases you would need those things. What I've found over the years is that I've seen a very few pathological cases where Poisson distribution actually fits. Really, the rule is by far over dispersion, by far most commonly. Occasionally under dispersion, but usually over dispersion. Okay, so that's the general idea here. We need a way to break this bond, this link between the mean and the variance, which also happens with binomial, right? The binomial is n mu times 1 minus mu. So both of those have that strict link there. So over dispersion means that the variance is bigger than the mean. Under dispersion means it's smaller than the mean. Good names for those. And there's a couple different ways of handling this, of modeling this situation of over or under dispersion. Over dispersion is by far the most common, and it's also the easiest to handle, which is kind of a nice coincidence. There's a few different ways for handling over dispersion, which I'll tell you about. Now, any question about the idea of over and under dispersion? Everybody got the idea? The data don't necessarily, real data don't necessarily follow those relationships.
Hey, Gary.
Yes.
Why do we use those distributions at all if they're not like based in reality? Like, couldn't you get better distribution?
Yeah, well, that's actually exactly what we're going to do right now. Yeah, so there's a few ways to extend those distributions. So I think the reason there's a couple reasons I think they're used in practice. One is they have the correct sample space. Okay, so if you want to model non-negative counts, you need a distribution that has that sample space. So Poisson is a good building block for that. Today, we'll see several extensions of Poisson that handle these cases where it's not realistic. But yeah, the exact Poisson distribution makes some really strong assumptions. Same for the binomial, makes some very strong assumptions. So what we need is to use those distributions as a base to build on. Yeah, good question though. But yeah, actually, so just to continue on that comment a little bit, if I'm reviewing a paper and I see that somebody has used Poisson regression, I will ask them to justify it or suggest that they use an extension of Poisson that would handle overdispersion. Okay, but Poisson alone is rarely a great choice. Okay, what else? Other questions? Okay, so one way to handle this is to come up with exactly what Matt suggested, come up with another distribution that's like Poisson, but more flexible. And the most common one is negative binomial. And you would have seen this, those of you who took theory would have seen this distribution in a very different context, but it's also used here to model count data that have a variance bigger than the mean. Okay, here's the mean. If mean is mu, then the variance is mu plus k times mu squared. If k is positive, then the variance is always bigger than the mean. Okay, so this can handle over dispersion, but not under dispersion. It's also an exponential family distribution with an additional dispersion parameter k. And that can be estimated by maximum likelihood. Oh, and here I'll tell you how the distribution. So there's, those of you who took theory, if you remember, the negative binomial, I believe, is the number of coin tosses you have to make in order to get a pre-specified number of heads. So binomial is you have a fixed number of tosses and you're counting the number of heads. Negative binomial reverses that. It's the number of tosses you need in order to get a specified number of heads. So it could take infinitely many tosses. So that's why it's the correct sample space, 0, 1, 2, up to infinity. Okay, that's all fine. It's not a useful way to think of negative binomial for generalized linear models. A better way to think of it is that it's a Poisson distribution where the mean is allowed to be a random variable. Okay, the mean is, if the mean, and there's some nice choices, if the mean is assumed to have a gamma distribution, then the resulting compound distribution is a negative binomial. And if you parameterize it that way, the mean is mu and the variance is mu times mu plus k mu squared. Okay, everybody get that idea? And this is actually usually physically the way overdispersion happens, right? If you're looking at overdispersion, say you're looking at, say, the number of arrivals at an emergency room each day. So that's your outcome. Could be 0, 1, 2, 3, 4, could be a really large number, okay? Exponential assumes that every person is the same and they have the same likelihood of appearing at the ER. Well, that's not true. People are much different. Some have a much higher probability, some a lower probability. And so by making the mean different for each person, that's how you get a more flexible distribution than negative binomial. Than Poisson, sorry. Another way to think of it, if you need even another way to think of it, the problem with Poisson is it only has one parameter. So how can you model both the mean and the dispersion? We've now added a second parameter. This k is now your second parameter, and it allows the variance to be different from the mean. Any question on that idea? Okay, if you go back to theory, you can do the integrals and get the get the probability density. And one nice thing about this is that it's in closed form. You can actually write this down as a probability distribution and in closed form, which we'll see is not true of some of the other ways. Okay, you can do a similar thing here with the binomial distribution. Same thing, it only has really one parameter, but you can assume the mean, the probability is a beta distribution, and that gives you a beta binomial, which is a more flexible distribution than binomial. Same sample space, but more flexible. Same thing in closed form version of it. Any questions on this? Okay, so this is method 1 for overdispersion. Method 2 is also based on additional random variables, can only be used for overdispersion. But here's a model at the bottom of the page here. Y has a Poisson distribution, mean is x prime beta plus epsilon. And that, what is that? What's the function? What's that? How is that plus epsilon going to help us? Actually, first, remember I said we shouldn't use plus epsilon above? We were talking when we started the class, I said you shouldn't use plus epsilon, and now I'm using it. How come it's going to work this time?
It's going to turn your mean into a random variable again.
Yeah, it's a random variable.
Values.
Exactly, it's a random variable, but look where it appears. It appears in the linear predictor, which then gets linked. The linear predictor can take any values, right? So there's no problem there. But it does exactly what Carrie said. It allows the mean to then become a random variable, changes for each subject, and it accounts for subjects that have greater or lesser likelihoods of events. Okay, so long as that epsilon is in the linear predictor, we're okay. If it was out here outside the Poisson, it wouldn't work because we wouldn't get count outcomes. Okay, everybody get the idea? So it's similar. Instead of based on gamma, it's based on normal. Same thing with binomial, you can do the same thing. Okay, so why would you use gamma and why would you use normal? What would be the advantages of each of those? Turns out they're each useful in different situations.
A question.
Sure.
Must we specify the parameters of the epsilon, like must it be standard normal, mean 0 and variance 1, or how do we work with it?
Yeah, good question. It needs to be mean 0. Well, it could be a different mean, but the mean would just get absorbed into the intercept of the linear predictor. So usually it's assumed to have mean 0, but it can have a different variance. And in fact, we need it to have a different variance. Otherwise, right, the problem with the Poisson is it only has one parameter. So if we don't allow another parameter in the normal, we won't have the second parameter to control the dispersion. Okay, so that's exactly right. Is that we need, usually it's assumed it's simpler to assume it has mean 0, but it's always assumed to have a variance that's not necessarily 1, and then we'll estimate that variance. Okay, good question. Anything else?
Question, Gary.
Yep.
So if you're adding this random variable to your linear predictor, you're essentially adjusting the variance, but since it's still a Poisson distribution, you're also adjusting the mean. So the mean is going to change. And so your estimates change.
That's an excellent point. So the parameter estimates can change a little bit, exactly, and which is appropriate because if you had the wrong distribution before, your estimates were probably wrong.
Okay.
So in fact, it is correct that the estimates will change. Usually the betas don't change a ton, but the intercept can change. Actually, there's a weird thing that happens with this. It's a log norm. It turns out there's kind of a little bit like a log normal distribution. There's a sigma squared over 2 term that appears you have to be a little careful with. I don't think that's what you're asking about, but yeah, I think in your with your question, the issue is that that yeah, the betas can change a little bit, and that's a good thing.
Okay.
Yep, good question. What else? Okay, turns out there's some pluses to the gamma approach. It can be calculated in closed form, so numerically it's easier to work with. They're both flexible. They both add 1 parameter for dispersion. One of the downsides of the normal approach is that it does not have a closed form, which numerically means it's much harder to work with. So you can't, what that means is you can't actually calculate this probability density. What needs to be done now is a numerical integration over the normal distribution. Okay, so numerical integration is kind of like the trapezoid rule. If you remember calculus, kind of divide a normal distribution up into trapezoids and take their areas. Okay, numerical integration, just a more sophisticated version of that. But what it means numerically, now think about your algorithm. You have an iteratively reweighted least squares algorithm, and at each function evaluation, you have to do a numerical integration. So it was really fairly recently when there was decent software. ProcMix was probably the first, in SAS, probably the first really good software that would do this. So, but yeah, that's a major consideration, okay? So why would anybody ever do it this way? If it's so much harder, why would anybody ever do it this way? Well, one of the nice things about having epsilon being normal as a plus normal is that we now have all the tools for normal modeling. If you want time correlation, you can make epsilon an AR1 process, an autoregressive process. If you want random effects, you can make epsilon constant for groups of subjects, like families. Each family could have their own epsilon. That would be a random effect that would account for family correlation. There's not really a decent way. Well, there are some ways, but they're not as clean and intuitive, and we don't have as much machinery to do those things for the gamma approach. Okay. Any question on that? In fact, there's a few nice papers. I think I remember, let's see, authors, I think Molenberg's, which combines these two. So it'll make the base model a model like gamma, so it's easy to handle numerically, and allow random effects using the additive normal form. Okay, so that's a nice kind of a hybrid, which has some advantages.
Hey, Gary, I have a quick comment.
Mhm.
So the R package that you list below didn't work for me. It gave me the same results as the first model. So I had to write a custom link function to do this, which wasn't practical.
And did I give it here on this page someplace down
Yeah,
below?
it was the same. It was the same page. So right under the SAS proc NL mixed.
Oh, GLMMML. Let me think about that. What does that one do? I thought that one did logistic regression with random effects, but I don't know, now that you say it, I don't know if it does Poisson regression with random effects.
It does do Poisson regression with random effects.
Okay, but what was the trouble?
So the trouble was our first model in the homework doesn't have like a random effect specified in it. So it's just a generalized linear model.
Mm-hmm.
This one requires you to add one. And even if you add one, you get the same results as the first model. So there's no handling of over dispersion using this method of GHQ. And so to actually fit it in R, I have to write a custom link function.
Yeah, you don't want to do that. Let me think about that for a second. I think maybe since I wrote these notes, there's a newer R function. I think it's in the LME4 package, and I believe it's called NLME, nonlinear mixed effects. And I believe that one will do it.
Okay.
Yeah, I don't remember that as with GLMML. I don't remember that issue that you're talking about, but I'm not saying it didn't. I don't remember it well enough. Yeah, but an alternative, yeah, would be LME4 package and LME.
Okay.
Yep, take a look at that one. Sorry about that if I
No problem.
gave you bad advice. I don't. Oh yeah, you do have in the homework. You do need to do one of these. Yep. So in the homework, by the way, that Jonathan's talking about, you'll be fitting, I think, 4 models: a standard Poisson model, and handling over dispersion with each of these 3 approaches I'm talking about now. So you'll be fitting these models. Oh, also, Jonathan, I think I've got a handout coming up. I think Matt would have posted it last night on handling over dispersion in SAS and R.
Okay, I'll take a look at it.
Yeah, sorry about that. What else? Anything? Okay, so there's a third method I want to tell you about, which is quasi-likelihood estimation. Again, this is another method for handling over or under dispersion. It's quite different. And, you know, the previous 2 had to do with making the mean random, either by adding a gamma distribution or a normal distribution. This is very different in flavor in several ways. So the thinking was, and by the way, this was published essentially at the same time as the generalized linear models, the Nelder and Wedderburn paper in 1972. This was in 1974 by Wedderburn, and it really followed directly on with that. It was in the original GLIM package and everything, really, really nicely done. So what they do in this case is assume that if the problem with the variance is that it's too restrictive and doesn't have another parameter, it just adds another parameter. So it says, well, the problem with the Poisson is the variance is equal to mu. So let's just say the variance is equal to phi times mu. Phi is that additional parameter we need to break that bond between the mean and the variance. So what's the problem with that? That should work great. We've got the additional parameter we need. If phi is bigger than 1, we get over dispersion, right? Because then the variance is bigger than the mean. If phi is less than 1, we get under dispersion. The variance is less than the mean. So what could go wrong? Well, it turns out it's not that it goes wrong. It's just they do have to do some extra work. It turns out there aren't really probability distributions with these properties. So in other words, if you say, I want a Poisson distribution with mean mu and variance phi times mu, well, you're out of luck, right? The Poisson distribution has mean mu. You can look for an extended distribution, but there's really not a decent one around. So what you give up in this case, what you gain here is something very simple form, very simple to state. It allows under dispersion, which the previous 2 methods do not, right? Do you see intuitively why the previous 2 methods cannot handle under dispersion? The previous 2 methods make the mean random. So you can only add variability, right? You can't make the mean random and take away variability. So the previous 2 methods, the normal and the gamma, can only handle over dispersion. This one handles under dispersion or over dispersion. Okay, what it requires, the downside is you don't get a probability model. And I'll talk about what that means here in a second. But the immediate problem is how do you estimate the betas, right? That's what regression is all about, estimating the betas. So what it turns out is that there's a modification, and actually not a huge modification, of iteratively reweighted least squares that can do the estimation in this case. It's super clever. They realized that even though the model is specified a Poisson distribution, the estimation algorithm never used that. It uses the relation between the mean and the variance and the link function. So in fact, we can specify any variance we want and just work through that algorithm just like we usually would. Okay, so it's a bit modified. This is called quasi-likelihood. Usually in software, you'll say quasi-Poisson, or in SAS, I think you specify p-scale or d-scale, just, yeah, d-scale and GenMod to specify that you're adding a scale parameter. Okay, everybody kind of see what this is? It's kind of an empirical hack, but it has theory behind it. Okay. Any question on this basic idea? Okay, here's a few features of it. It turns out that in this case, and remember Jonathan's question a few minutes ago, the betas change when you add those normal distributions or the gammas. That's actually not true here. The betas don't change, but their standard errors change, and they'll change proportionally to the square root of the scale factor. So really, this can be viewed as Poisson regression, but adjusting the standard errors. And this makes intuitive sense, right? Because if you've got more variable data, then your estimates should be more variable, so you need wider standard error. So the intuition works okay. Okay, any questions here?
Hey Gary, I have a quick comment. So I was reading that they are kind of deprecating the term scale parameter and they're using dispersion parameter instead. So you only see scale parameter in like older software.
Okay, good. I hadn't seen that. Yeah, I think, actually, I can't remember. I think it was called a scale parameter in the original papers. But yeah, good to know that. I think, I want to say R has always called it dispersion, but I'm not sure about that either. Yeah, good. Thanks for the heads up. What else? Anything else? Okay, so let's get pluses and minuses of this compared to the previous two. What's an advantage of quasi-likelihood compared to the normal or gamma methods? There's one big advantage.
It allows for under dispersion.
Exactly. It'll handle under dispersion. Okay. What's a disadvantage? Well, one disadvantage is that it's not an actual probability model. So for the early people working this out, it was a disadvantage because they had to rework all the equations. Iteratively reweighted least squares had to be redone, had to develop a theory of quasi-likelihood because it's not now maximum likelihood anymore because there's no density, so you can't write the likelihood. Okay, all of those things have been done. One of the other disadvantages comes, say, one of the things I like to do with new models when I'm working with new models is simulate data and then fit the data and make sure I can recover my original parameters. I do this all the time. One of the problems is that I can't simulate data from this model because it's not a probability distribution. So there isn't a function in R that says R quasi-Poisson, random quasi-Poisson. You don't really have those things. So, so I think that's a disadvantage of this approach. Okay, those are to me the main pluses and minuses. Okay, those are the three, and I did give you, actually, let me jump over. Now, any question about this? 3 approaches, you're going to use them all on your homework with the serial data. You're going to fit some models to the serial data. You're going to use all 3 of these approaches plus a standard Poisson generalized linear model. Any questions about this? Okay, again, this is, I always assume under or over dispersion in practice.
Question.
Oh, sure.
So in the additive case where we add the epsilon, and you said we estimate the variance. So I'm trying to imagine it's like we are going to simulate that epsilon. So for us to do that, how do we estimate variance yet we don't have any information about anything?
Yeah, so you to simulate data, you would draw a random normal, and then epsilon, and then calculate x prime beta. If you're simulating, you know the x's and the betas and sigma squared. So you'd simulate epsilon, calculate x prime beta plus epsilon, exponentiate it, and draw a random Poisson from a distribution with that mean. Okay, so simulating is pretty straightforward because it's a probability model like that. Everybody okay with the simulation? Okay, to fit the model, this is where it gets tough, and this is why you need so much both statistical theory and numerical analysis to be able to fit this. It can notice, you know, the model. Think about it intuitively. You could take the mean of the data. Say you just had a beta 0, no betas. You could take the mean of the data, and that would give you a decent estimate of something related to the mean. And then you could look at the variance compared to that mean and notice it was larger. And based on how much larger the variance was than the mean, that would tell you how large sigma squared is. I'm just talking intuitively now, okay? So the information is there by looking at how much bigger the variance is than it would be expected to be under a Poisson distribution, okay? And then all the rest of the machinery to do maximum likelihood, the quadrature for the numerical integration, the iteration for the Newton-Raphson, all of that stuff is done with theory and software, okay, to get actual estimates of sigma squared. But intuitively, you see the information is in there. Okay?
Thank you.
Sure. What other questions? Okay, I was going to jump over to software, but while I'm here, I'm going to talk a little bit about references. I haven't pointed this out, and since we're on this page, it'll save me another screen sharing attempt. So this is the key paper, the original paper. It's actually a really cool paper to look at because so much of the ideas and software are still there. 48 years later? It's just a landmark paper. So Nelder and Wedderburn, 1972. This quasi-likelihood was then developed in 74 by Wedderburn, followed up on this original idea and extended the Newton-Raphson approach for this situation. So those are the 2 key theoretical papers. The first big paper on the first big book, classic book, was Nelder, McCullough and Nelder, came out. There was an earlier edition. This is second edition. That one's still a classic. I learned a lot of stuff from the SAS documentation, generalized linear models. I think the SAS documentation is really good on that. Matt's recommended the Agresti book. I'm not as familiar with that. I think Dobson is a really nice kind of very hands-on applied book on this. And then this one is kind of interesting historically too. The other cool thing, you know, now everybody puts out R packages when they publish a new statistical method. They'll put it in an R package with it so it can be disseminated. Well, they did the same thing. You know, almost 50 years ago, they released the GzLM package, which was, I think it was Fortran based, and it was a package that fitted generalized linear and quasi-likelihood models. So you could run it. It was actually a pretty frustrating piece of software because you would run it. You'd go to all the trouble to set up your data and run it, and your printout, your entire printout would be deviance equals degrees of freedom equals. No betas, no diagnostics, no nothing. So you really had to pry for all that. So it was in there. You had to pry for it. But in terms of fitting models, it was a nice, clean way to do it. And that algorithm is still the one that you'll find in any statistical software that fits these models. Okay, so a little bit of history there and references. Any question about some of this? Okay, we've got a bunch of handouts I'll show you now. I have to see what I can find first here. How about this one, software in R and SAS. So this is, remember I gave you a handout last time that looked quite a bit like this. It had software for fitting Poisson and binomial generalized linear models. This one extends that handout to overdispersion. So here's your basic SAS and R for Poisson models with no overdispersion. Remember, there's your covariates, so that's the systematic piece. Your random piece is Poisson. Am I sharing this? Sorry about that. Is this shared? Can you see this handout? Okay,
No.
Sorry about that. That was my fault. Nope, wrong one. There you go. Okay. So here's the SAS and the R for Poisson. You've got your covariates, systematic piece, the random piece is Poisson, and the link function is log. Okay. To do quasi-likelihood, there's a restatement of the model. And in ProcGenMod, you specify p-scale. It's a keyword. SAS tends to work with keywords. P-scale or D-scale will tell it to do quasi-likelihood. In R, you would use a family of quasi-Poisson. But those are really the only differences. Okay, with the normal error model, y given epsilon is here's your model, that same model we had before. And one way to do this is proc NL mixed. NL mixed is SAS software that allows normal random effects. So you can actually just write out the model. I like NL mixed in this way because it writes out the model. Here's your linear predictor. Poisson y is distributed as Poisson with mean e to the linear predictor plus epsilon. Epsilon is normal with mean 0 and variance sigma squared. So it's exactly like you write it with pencil and paper.
Would the beta coefficients on this still be on the log scale, I'm guessing?
Yes, they'll still, exactly. All the beta interpretations for all these models are the same. So e to the betas for Poisson-based model, actually the beta interpretation has to do with the link function, not the probability distribution. We're not changing the link function here. Good question. Okay, in R, it's the same kind of thing. You have to find a way of specifying the random effect. And here, this is the syntax for GLM and ML. And here you go, Jonathan. So I'd misremembered this, Jonathan. It's GLMER in the LME4 package that fits these generalized linear models. I
Right,
think I,
there's still, but Gary, there's still the issue that you're fitting a random intercept on the ID. So in the models that we're fitting for homework, there is no random intercept.
yes, but there is. So that's a great question. So there is up here, there's a random intercept, but notice the subscripts. I see your question now. Sorry, I missed your question before, I think. Look at the subscripts. Subscript I, so there's no J's in here, right? This is all totally independent data. You only have one subscript I, so each subject gets a new epsilon. Okay, the epsilons here are not used like a usual random intercept for clustering. They're used for over-dispersion. They're used to inject more variability into the model. Okay, so each subject gets its own random intercept. Each observation gets its own random intercept. Okay, does that help? Was that your question?
I'm still not understanding because so over here you're clustering by an identification, whereas in the data that we have, since we are only looking at the first child or the family member equals 3. And for the previous models, there isn't any specification of any repeated measurement or any grouping factor. So do all of the previous models need to be grouped by these subjects, by these different subjects?
Well, you're only picking out, no, actually, this is the only one where you need to do that. And you're picking out only one child from each family and only the baseline times. So you have no correlation within families or over time. So what you're using that ID for is each subject will have its own unique ID. So you're telling the software to add a random effect for each observation.
Okay.
Yeah.
Okay.
Okay. See the difference? It's actually, it's exactly the same phenomenon as clustering. It's just that in this case, we only observe one observation per cluster. So we can't estimate the within subject clustering. We can still estimate variability, but we can't estimate correlation.
Okay.
Okay. Yeah. Thanks for staying on that. Yeah, I think I got it. Okay. Same thing here with negative binomial error models. You've got in NL mixed, you actually specify the density, the log of the density explicitly. You just write out the formula for the log of density, and NL mixed has a feature for a general likelihood models. GenMod, you specify negative binomial. In Y, there's a function called GLM.NB, I think is the easiest one I've found, but there are probably others as well. Okay, link equals log, so you're still specifying all the other parts of the model. Okay, so that handout will be, to put it mildly, it'll be useful for your homework. So what other questions do you have?
When you're actually describing these methods and you use them, are the error sigma and the K and the phi, are all those just like nuisance parameters and you don't actually talk about what they were estimated at, or do you?
Yeah, that's good. That's a really good question. What I usually do is report that I fitted a generalized linear model using a negative binomial distribution, and I probably would mention, I would probably have a sentence saying the negative binomial parameter was estimated as 2.5 with an interval of whatever, indicating substantial over dispersion in the data. I would probably say something like that. It doesn't tell you anything about covariate effects, but it does actually tell you something about the data that I think is useful. Yep, same thing with a scale parameter and quasi-likelihood.
That makes sense.
Okay. Yep.
Thanks.
Yep.
A quick question. Can we also fit like a nested model with the LME4 package?
I believe you can, but I think, okay, so this, Randy, I think it's Randy. So this is a good question, but the issue there becomes you end up with now, if you want to include overdispersion and nesting, the issue now becomes you have two levels of numerical quadrature. And SAS claims, ProcMix claims it can do this, or NLMix, I guess, claims it can do this. I have never succeeded in fitting even one model with that method. When I come back in a few weeks, I'm going to talk about Markov chain Monte Carlo, which is another method of fitting models like this with nesting, where you have two or more levels of randomness. Okay, so I'm going to put that question off a bit. I would not try it with this software. That's the short answer. Okay, so in other words, if we want to take into consideration families, I think Markov chain Monte Carlo is a better way to go. Other questions? Okay, I do want to show you one more bit here. Partly because I stayed up last night to do it, so I want to get at least 5 minutes of use out of it. Okay, so back to Matt's question. If Poisson and binomial are so darn unrealistic, why would we ever bother to use them? And the reason is because they form a basis for extensions to a lot of useful practical cases. This is the handout called Extensions and Applications of Generalized Linear Models. Okay, one of the extensions is to over and under dispersion, which is what I've been talking about today. So we've already covered that really, but I put it in here just to point out that it is an extension of Poisson. There's another idea here called an offset. It can be used for any generalized linear model, but really it's mainly for log-link models. And the idea is the Poisson model estimates a count of events per unit time. So unaltered, it assumes that the time length of all of your observations was the same. Every subject was observed for the same length of time. Well, anybody in epi knows that that's not going to work very well, right? That you just don't have data like that. So what do you do? What can you do when you have differing lengths of time? It turns out one thing you could do is just model the counts per unit time, y divided by t. The downside of that is that now you don't have integers anymore, right? Y over t is not an integer, so you can't use Poisson. You could try to use normal, but the whole problem in the first place is you had a highly skewed discrete distribution, so normal doesn't work very well. Okay, so you really don't have any very good options there. What's done instead is to actually incorporate the time length into the model explicitly. So if observation y was based on an interval of length t, you would expect it to have t times as many observations as it would if it were observed for 1 unit. So if t is equal to 3 years, you would expect 3 times as many events as in 1 year. So multiply the mean by t, and then a little log trick puts the t up here in the exponent. So really, log t is another term in the linear predictor, but it doesn't have a beta because you're assuming proportionality here. So that's what an offset does for you. It takes an exposure, or it could be area, could be anything like that, and it allows it to be incorporated into the model without a beta. And it's almost always used to adjust for differing exposures in log models, time, area, volume, things like that. Okay, super useful trick. Otherwise, your data just don't have much of a meaning. Everybody get the idea? Okay, software is easy. In SAS, you'd add a keyword of offset equals. In R, you add plus offset. That tells it not to put a beta. You can, if you want, By the way, this also works for negative binomial. So you can mix, you can have an over-dispersed model with unequal exposure times. Okay. So that's one extension, another extension of generalized linear models. And this last one, I only have time to very briefly mention, but I'll let you read about it. Maybe I'll talk about it next time I come back. These are zero inflated models. It's models that are used when you have counts or continuous positive values, and you just have way more zeros than you would think. And examples are, say you're looking at inhaler use in a population of kids, but a lot of kids are not asthmatic, so they wouldn't even never use any inhalers. So you'd have this big batch of zeros for non-asthmatic kids, plus the zeros that come from a Poisson or negative binomial, due to days when an asthmatic kid just doesn't happen to use their inhaler. Okay, so you see there's two sources of zeros, and the model has to be able to sort those out. That's the most common. I'll let you read about hurdle models, but these zero inflated models are very common. They're software form. Roughly, they're handled by saying, creating a mixture and saying certain probability that an observation is zero. And there's also a probability that for each value 0 up to infinity from the negative binomial or Poisson. And that creates a probability distribution based on a combination or a mixture of two generalized linear models. But it's still a probability model, so you can still fit it by maximum likelihood, and you're off and running, okay? So really all the previous machinery continues to work well. Any question about that? I'll just mention very briefly a case I've done a lot of work with. I actually have not worked that much with the count ones, but I've worked with a lot of cost data, and there the distribution is continuous positive, but it can be zero. An example here is healthcare expenditure, but when some patients don't use any of the service, they get zeros. This is actually an easier problem. It's still handled in the same way with a binomial part and a continuous part in this case. Instead of Poisson, it would be gamma. This is actually easier because you can only get zeros from the binomial part. You can't get any zeros from a gamma distribution. So you don't have that situation in the previous one where you get zeros from Poisson and you get special zeros, extra zeros, and you have to figure out something, how those combine. Okay, it's actually not that much easier or harder, same idea, mixture distribution. Any questions on that? I know I went over it too fast really to have questions. And then I'll mention this one when I come back, risk ratio and risk difference, because this is kind of cool. So I will mention this when I come back next time, talk about Bayesian. Sorry, ran over time again, my fault again, but it's a little hard for me to keep timing. This is a couple problems. One is I'm not so much used to teaching on Zoom, but also there are entire courses that cover generalized linear models. So I've tried to do an entire course in a couple days and had to do a lot of cherry picking. Anyway, I hope it's interesting. I really appreciate the opportunity to come in because this is some of my favorite stuff to talk about and to do. So appreciate the opportunity to come in. I'll stick around for a while if there's any questions. Otherwise, if you have questions, I'll be in on Wednesday for the office hour. You can feel free to email me with questions. And see you next time.
Hey, Gary.